Okay, let's get recording. So this is SDF 11. Alright, so let's take a look at what we got. Alright, so this is what we're working with, and it's kind of weird that all the cross sections are squares, but you have to think that it's not just a cross section of a single cube, it's a cross section of a space that's composed of a whole bunch of cubes stacked together. So if you think about it like that, I think that usually you would see maybe if you take a cube and you cut it at the corner, usually what you would get is you would get a triangle cross section, but we're not seeing a triangle cross section. Well, we are seeing some triangle cross sections, aren't we? We're seeing at some point in time. Okay, yeah. So as this moves, at some point in time, yeah, but none of the cross sections are equilateral. I don't know. It's just very weird. It's weird that I'm not seeing the kind of triangles I expect. Like right here, there's no equilateral triangle, but you'd think if we're approaching the volumes from the angle that we are, that we would be seeing equilateral triangles. So one of my thoughts is we're kind of we're not really doing a cross section into the corner of a single cube. It's like it's not even cross sectioning into a wall of cubes. It's like the entire volume that we're inside of is just cubes. And when you think of it like that, I think the cross-sectional areas just look different, because if there was just one single cube and we were doing cross-sections of it, you would probably get the shapes you're expecting from a cube cross-section. However, all the other cubes in the space, in the volumetric space, are probably occluding other cubes, right? They're all occluding each other, and because of that, we're probably getting cross-sectional shapes that we're not quite expecting. So even though this isn't what I would expect here, I think this might be correct. So before we continue, we're gonna go look for that dolly variable. And we're going to change it to be only positive, because I think right now it's like fluctuating between negative and positive. Yeah, so we have like cos I time. So that's no good. So we need something like a float 32, and we need like a pos cos equals the cos of like the cos of I time divided by 2.0, so we're going to smush it, and then after we've smushed it on one axis, we'll do plus 1.0, right? And we'll, now if we want to check to make sure that that math right there is correct, we can go take a look at, say, like desmos.com and just check that out. So let's go to desmos.com and look at their calculator really quick. I don't know if this is gonna be very favorable on a monitor like this, but let's just see if we can smush this in here. So if we have the cos of x, that is what I expect, and if we divide that by 2, so we take the cos of x and we divide it by 2, so cos of I time will be our x, and we'll divide the result by 2, and we kind of smush it on, we smush it, actually, do we really want to smush it like that? Hold on. So the cos of x. Actually, really all we want to do is add 1, don't we? Oh no, because then that is ranging, if we look in here, that's going between, um, 0 and 2, right? So the range between -1 and 1 is 2 units rather than 1 unit, right? And so that's why we're going to take the coast curve and we're going to smush it first. We're going to smush it down. And then after we have that, we're just going to add 1 to keep everything above 1. So do that. And now, that isn't correct either, is it? Okay, I'm gonna have to move this onto another screen where I can actually see what the fuck's going on, because... So let's see, I took it... Okay, so when I... Oh, okay, so it's actually plus 0.5, it looks like. So I made a mistake. So if we add 0.5... Okay, yeah, so it's the cos of whatever, and then not plus it's plus 0.5 like that. So I'm going to take that, and I'm just going to put that little note in my shortcuts. So we have a positive cos, and we're just going to say pos cos, and pos cos, and pos cos. And then we'll just take that right there, and, you know, I kind of understand that this is a type def for float 32, so I'm not too worried about that. So pos sin would be the exact same thing, but we're going to use sine, so we might as well make that as well while we're here, right? So we'll put this into our shortcuts, and pos sin, and then the sine, right? Sin, sine, whatever. Okay, so now we need to look at this graph here, and we need to do the same thing, but we need to figure out, well, what about if we want to go negative? So if we just, if we want to keep this range always negative, can we just do a minus 0.5, and that'll get us to where we need to be, and I think that will work. So let's give that a shot and see what we can do. So what the hell here? Okay. So with that, does that look like the correct range? And looks like, yeah, that goes down to 1. So yeah, so we just need to take it and minus it if we want to get the negative versions of these. So I'm going to do the same thing. I'm going to cut, paste this, and we're just going to replace everything that says positive, and we're just going to replace that with negative, right? So we'll just do neg, copy that there, and then we'll just paste, paste, and paste, and paste. Oh. And it looks like we made a mistake here, so let's delete that. And then with these, all we got to do is we got to take the 0.5 and just make that into a minus. And now we have some nice formulas for negative cos and positive cos. Those are not scientific terms or whatnot. It's just so that I kind of like understand what we're using it for, right? So the reason I did that is because for this dolly, the dolly right now is going backwards and forwards. And if we look at the screen over here, we can see that sometimes we're seeing this green section, cross-section, and then sometimes it's like disappearing. And what I want to make sure of is that moving the camera forward is what's getting us this green to show up, right? If moving the camera forward is not what gets that green to show up, then our normals or our camera plane position is somehow in the wrong position. So we're just going to take this and we're going to try to rerun that as it is and see how that works. So take this, Control A, Control Copy, Control V, hit enter, and just see if that works for us. So now, much slower, right? And that's because, well, why is that slower? Well, you saw when we took this graph, that this graph, when we divided by 2, we kind of smushed the curve, and so the up and down fluctuation was less extreme, less steep. So that would make sense that this is slower moving. But also you can see that now there's mostly only green showing up everywhere, right? Like there's a little time afterwards but it's mostly the green section is showing up. Now, if we did the if we did a negative cos for a second, so if we did neg cos, and then we just did this right here, and if we take that and put this in here, I'm expecting not to see any green, right? So I'm trying to form these hypotheses and test my hypotheses to see if they are correct before continuing, because I want to be working on a solid foundation, right? We need to have an accurate model of what's going on before we can continue coding, right? And, you know, so I'm trying to keep the science in computer science. So, we can see that when we use the negative cos, where we're just fluctuating between 0 and a -1, that we're not seeing any of that green. So we're not seeing any of the voxel map bounds. So that tells me that I'm looking at what I think I'm looking at, despite the cross sections looking a little bit strange, right? So let's redo that, and okay, that looks good to me. And this was an optional section, right? Use animated dolly for debug. Okay, so I know we had another optional section somewhere around here. So zoomed in camera. So what kind of camera are we using here? Sure, I don't really care about the zoomed in camera aspects, but we're gonna turn off this animated dolly now, because we kind of looked at it and we've decided, you know what, that looks good to us, and let's just continue from here. So this is where we're at. We see this little green speck because our camera plane is like intersecting the very tip of our voxel map volume at a 3/4 perspective in terms of the tilt, or a isometric perspective. Is the camera is tilted in an isometric perspective. So with that, we can kind of start marching and kind of figuring out, like, okay, how can we render more than just this, right? And we got a lot of stuff here. So first thing is, well, max steps is probably where we want to be if we're trying to look for this code. And we can see that if the voxel is not empty, ray march inside of the voxel, right? So we have this thing here. And what else do we have? We have the slice render, if slice render. So this whole thing right here is, well, that's a lot of stuff. Okay, so the slice rendering was just to, color code the voxel tile X, tile Y, and tile Z that we were inside of, to kind of visualize that space. So all of this code right here is just for visualizing visualizing how things are working, right? So if we take this out, we're not gonna see much. So it's gonna get scary, but you know what? We got a new file and we're ready to screw some things up. So what we're gonna do is configuration slice render, right? We're gonna take this and we're just gonna remove that. And so we're going to take that out, and we're going to save that, and we're going to rerun it, and we're going to expect to just see probably like a black screen or a solid color now. Okay, so we see this solid white, and before we continue, let's look at where that's happening. So we had like a debug only section right here, and that was like the all white, and we really want to remove that because now let's look at this marching. So we're marching, and the first thing we do is we just want to we're just trying to figure out what voxel we're currently in, right? and the distance to the next. Okay. So I kind of think that this distance to the next is probably not calculated. I probably stubbed it in, but I highly doubt that I actually calculated that value. So if we look at this, we can see this next. Yeah, I would say that this the voxel distance object here. So I don't think anywhere that we're actually using this. So I see. So this right here is where we're kind of getting all that information. So let's look at that for a second. And so we can get the voxel cell value that we're in. Yeah, so to figure out the distance to the next voxel. So right here is kind of like where we have to figure that out and figure out, well, how do we know how to get to the next voxel? And do we even care about that? So you know what, the first thing we need to do before we worry about ray marching inside of a voxel is just being able to, like, hit the voxel, right? Hit the voxel, and if we hit a voxel that's not empty, we'll just render it as a solid color, and then we'll be done with that ray marching for that pixel, right? So that makes sense to me. Now, let's think about the naming here. So, like, we have, like, Vox and Voxcur, and does that even make sense to me? Because I don't really think that naming convention makes sense, because where is Voxcur? So Voxcur and Vox distance, and Vox is, this Vox 000 just has, Voxcur is just a VOC, right, and VOD. So, I think it would make more sense to just, well, first of all, let's make sure we didn't screw anything up, because I know we, okay, so we're going to turn on, we're going to put a bookmark here. We're going to turn on back the slicing for a second, so that we can see kind of like, and the reason I'm turning this back on is just because I'm about to make some changes, and as I make these changes, I don't want the changes to actually affect the code. So I'm looking at this, and I think that I get why I call this Vox 000, because I'm like, I don't know if I'm going to change what this should be called later, so we'll just call it Vox 0000, whatever, right? And that's fine. Just because Vox for voxel is just a very generic name. It's a little bit too generic for my taste, because this whole engine is working with voxels. So there's the potential to have another variable called voxel something, right? So I don't want to be too generic there. So I think it might be easier just to say, so if we let's look for where, like, Voc is in our code. So is Voc in our code in any place where, or is Voxcur in our code anywhere? Okay, so as long as in VOD for voxel distance. Okay, so since those are kind of like make sense, I'm just gonna try to reduce some of the things that we have to remember by in terms of the variable names. So we're gonna make this actually a little bit more terse. So we're gonna take Voxcur, and we're just gonna replace it with VOC for voxel current, and we're gonna make sure to match the case. And anywhere we see Voxcur, we're just gonna replace it with this, right? So now that makes it a little bit more terse. It makes it a little bit harder to know, like, what the hell we're talking about. But the thing is it's a trade-off. There's a definite trade-off here where now when we're reading this code, we can't really make any assumptions as we're reading it. And there was a time when I thought, well, people should never make any assumptions about your code at all. But now I realize for people to get a rough understanding of what's going on in your code, being able to make assumptions is a good thing. However, there's also the fact that, I just want to keep things as easy to follow and reduce the mental search space. So even though this makes it a little bit harder to follow because it doesn't have like a very readable name, the variable's type and the variable's name are exact matches of each other. So that makes things a little bit easier. And I'm trying to prioritize being able to follow the data. So the most important thing to me is just being able to identify where things are coming from. Because their exact names are, like, when I'm trying to give them human readable names, that's a abstraction, an extra layer of abstraction. And it can be helpful, but it also takes time to invent those names. And it can just add another, like, layer of mental indirection and mental, like, interpretation. So, what is Vox? Well, Vox is technically not voxel current info. I mean, that's what I'm going to make it stand for. But Vox is just these variables, right? That's kind of what it is. And then VOD is, it's not really voxel distance info. It's this next variable and this ds variable, right? But we do want to know, like, why they're being used for what they're being used for. It's a delicate balance, right? There's no perfect way to do it as far as I'm concerned, just because there's no perfect way to do it because our minds are not perfect, right? If our minds were perfect, right, we wouldn't need any comments because we just understand the code perfectly, just as the machine can just run the code and do exactly what it says. Our understanding would be so perfect that we wouldn't need comments, we wouldn't need nice variable names, right? So the whole point of, like, trying to arrange our code in the first place is to somehow cope with the fact that we're fallible humans. So how are we going to figure things out, so Vox. So Vox is voxel current okay, and VOD is voxel okay. And so we're not really sure about how we're going to implement this part yet. But we really want to figure out how to get this next variable. So the distance to the next. So since we've made these variables much more terse, we can kind of afford to stutter now, right? Because now that this isn't called, like, now that this variable here isn't called, like, voxcur or whatever the hell it was called, or this one, I think this one was called voxdis, voxcur and voxdis, right? Vox_dis. Well, now we can kind of stutter again. We can go dis next like that, because originally we had something like vox dis dot next, and we didn't want to make something like this because that's that's an extra redundancy where we're kind of stuttering, and it's not very useful, right? It can kind of be useful. I do like redundancy in some aspects, but today I don't. So, but now that we're calling voxdist just VOD, now we can do this dist next like that, right? And the reason for that, for wanting to name it in a less terse way, is because the further from the top level, the less frequent the reference, right? So since these are top level things, top level structs, they're going to be referenced very often, right? And just as in a natural language where you want to make words short that you use very often, same thing with code. So because this variable is kind of nested pretty deep, we want to make sure that we give it a slightly longer name so we can kind of find it easier. So we see that there's this this right here, and this looks like the only place it's used. Oh, it's used in a few more places, so we'll call this distance next. And then it looks like we have this as well. Okay, and then so this distance to surface right here, we'll call it dist to surface. And then we'll look for the ds in the code, which is a commented out piece of code, but we'll change that. And then dist next. So now that we have it as a variable like this, it's a little bit easier to find all the references, because eventually just having a variable called next, well, that could be a variable in a linked list or something, you know? So we want a kind of a more detailed name so that we can kind of find it easier. So this distance to surface, let's just put that back in the code, even though we're not using the variable right now. We're eventually going to use it. So take all that, and let's just make sure that we didn't do anything really stupid, and make sure that still runs. So, still runs. I'm satisfied we haven't done anything totally, like, code breaking. And let's try to figure out this distance next thing, right? So let's go over to figure out the distance to the next voxel. So the first part is just knowing what voxel you're currently in, and we kind of like already have that information, right? Because over here over here, so we have tx, ty, and tz, and this is how we know what voxel we're in. And then over here is where we're deciding, are we inside a voxel that's actually inside our voxel map, or are we inside a voxel that's like out of bounds? So remember, we're taking the entire coordinate space, the infinity of all the coordinates in existence, and we're just slicing everything up into voxels. So even voxels that aren't going to be rendered, we're gonna make even empty space into voxels, just to like make the space uniform and easy to work with. So when we're in bounds, we're actually inside of the voxel map, and these are just voxels that are like, you could call them like void voxels. It's like in the outside of the bounds of the voxel map. So let's see, what are these? So distance 2D and distance 3D. Okay, so these are where we're calculating the index of the voxel. And there's no index calculation here because this is, once again, it's outside of the bounds of the voxel map. So we're just going to set all these to 0, especially this flag value. So we're saying that no voxel exists. So has, I use has just because it's a 3-letter word. And you've probably noticed that I like 3-letter words. You could think of has as a dot exists if you would like to, if that makes it easier to think about. But yeah, so now that we're kind of here, we can kind of think about how do we figure out the distance to the next voxel, right? And let's just draw something and see if I have any paper that I haven't drawn on already. Oh man, I've used like I've used all sides of my graph paper, which is good, because that means I'm not being wasteful, but it looks like it's all used up. I could use some of this stuff. I don't know what this is. What is this? Okay, yeah, let's just use this. So, wait. Okay, I found a piece of graph paper I haven't used yet. So, let's break out the camera and let's just try to think about this, right? Let's try to think about let me just go back here. Okay, so I'm going to think about it for a second. And, actually, I need to go to the bathroom. So, I'm going to take this little diagram into the bathroom with me on a bathroom break. And maybe when I come back, I'll have, like, the correct answer. So I'm just going to set a timer for, like, 15 minutes. And I will think about what's going on here, and hopefully I'll be back with an answer. Okay, so I'm just gonna do this. Alright, so, okay, you have sound, I just don't have sound, okay. Where is my, oh, I can muted my sound. Okay, so, the answer to our problems is pretty simple. And I'm going to draw a diagram of that into the source code so that we can kind of know what's going on here. So, if we have our voxel and we're inside of it, so we're inside this voxel and we have like this line and we're like, we start from maybe here and we just do so let's say it's something like that, and it's like, how do you know that you're going to hit this point, right? And the first thing is that we can take the distances to different sections, right? So we can take these distances here. And we don't want to do the goal would be to not have to do the negative distances, right? To be able to use the right distances, and we'll figure that out as well. But right now, let's just draw this out. So let's put like little dots for these distances because they're like, or can we make this dashed maybe? Yeah, just a little dash. Make that a dot. We're gonna need more. Okay, so something like that. And this is point P right here. And we want to figure out this point here, which is point I, which is like our intersection. And the question is, how do we figure out where to get to here, right? And the first thing we need to look at is the x and y bounds. So we have kind of like a, over here would be our y bound. And then we also have like a, over here we have another, we don't really have a, but this line right here is the x bound, right? So x bound. Right. And so we have, can we try to make this double thickness? No, we can't really make it double thickness. We can try to make it triple thickness though. And take that. So we have these bounds, the x bound, which is going through here like that. And try to make it a little bit more, don't know if I like that, but alright, let's just keep going, right? So we're inside of the voxel here, and we want to know if where point P is going to hit, and is it going to hit over here, or is it going to hit like over here? So the first part is we can just do a min, right? So so we need something like if P dot, if x bound, so if x bound dot, if x bound minus P dot x is is there a better way to do this? Okay, we'll solve it the way we can solve it, and we'll try to figure out something better later. So if x bound, so if this delta, right, is less than is less than y bound dot minus py, right? So this point, so we're going to take this, we're assuming that that the rays are going into the positive space, that the rays are marching further and further into the positive space, and we'll account for that later, but for now we're just going to assume that they're always marching into the positive space. And so with that, this number here is going to be larger than p dot y. The number here is going to be larger than p dot x. Therefore, that's why we're going to take it like, do the subtraction like this, so that we can observe the difference between the deltas. Okay, so if it's that, then we're either going to hit the x, or possibly we're going to hit the z. So let's say for these boundaries, I believe we're using float 32s for the calculations. So let's make some float 32s. And we'll do like float 32, and we'll do we'll do dbx for distance to bound x equals x bound minus p dot x. And why we're going to make variables for this is because we're going to have to reuse some of these in our calculations. We don't want to have to like recalculate if we need it more often. So so distance to bound x, distance to bound y, distance to bound z, right? And then we'll take these and we'll just do that. And then, you know, x, y, and z. So, now it might be a little bit easier if we do db x, y, z like that. Yeah, that might be a little bit easier just because we can, if we can make all of these lowercase, it might be a little bit easier since the x, y, z aspects of a point are already kind of lowercase. So let's just say x, we'll call it x bound like that, x bound and y bound. And this point here, we need to figure out, well, what is this point right now? And we should already have kind of a, okay, so this xyz is our point. So instead of just creating another variable, we could use a define for this if we wanted to match the diagram here. So this diagram right here, we could do something like define p, and then just make it xyz, right? And that way we have kind of a way to think about this. So, and then down here we'll do a undef p, and we'll try to segment this into a way that is going to be a little bit easier. So let's do dist to next voxel, right? And okay, so we're kind of creating a new section in the code for the distance. So we get current voxel cell, get the current value of the voxel, and then the distance to the next voxel is the code right here. So now we can think about maybe indenting things properly. Maybe, well, first of all, we need to write some comment characters so we can keep this diagram in our code. So we'll just do that right now. And the next thing we might want to do is put the, do we really want the define right here? It kind of makes sense more here, just because like this might be a little, I don't know, this might be a little bit ugly. Like maybe we don't want to do it that way. I don't know. It's not too big of a deal. Let's just keep it here for now, and we'll just know that point P is that XYZ which is the XYZ coordinate of the camera ray, right? So this is the camera ray's position, and this is the camera ray's normal. So with that, we can kind of like change this around a little bit. So we can just say that if dbx is less than dby, I'd really like to... So let's do this. dbx is less than dby, and dbx is less than dbz. So this is... We're going to create, like, less efficient branching, maybe. We're going to create less branching. We're going to... rather than nesting the branches, I would rather just do an and have just one case for everything, so we don't have to get nested super deep and get all like confused, if that makes sense. So this is when the thing is, if we just use less than, we're going to cause some problems if it's less than or equal to. So less than or equal to, it's like an arbitrary decision, right? So we'll do dbx less than dby, dbx less than dbz, right? So this is the x bound is closest, right? And do we want to say, I don't know, else, and then we'll just take this code and we'll kind of cut paste it a few times. And then else, this would be an error right here. This is a, you done messed up. So dbx, dby, or sorry, dby and dbz like that. So we're going to do x, y, and z in that order. And then we have to make sure we're comparing it to the correct thing. So x compared to y, x compared to z, that's good. Y compared to itself, no dice. Y compared to x, y compared to z, that's good. Z compared to y, and z compared to z, that's bad. Let's change this to x and that to a y, right? So x's, y's, we can also make sure that they're balanced, right? Because we're going to expect the exact same amount of everything. So there's 4 cyan, there are many more orange. That already has me a little bit concerned. So 1, 2, 3, 4 yellow. 1, 2, 3, 4. Oh, wait, never mind. I just can't count. 1, 2, 3, 4 orange, 4 yellow, and 1, 2, 3, 4 cyan. So there's an equal balance of everything here, which is just a way to give us a mental checksum to be like, yeah, this code is probably correct. The next thing is, this is where we're looking at x's, and x's is less than, y's is less than, z's is less than, and then we need to look at the second component and make sure that the second component is always different than the 2 colors here. So cyan, 2 different colors, orange, 2 different colors, and then we have this yellow here, and then we also have 2 different colors. So that looks like we haven't made any transposition errors, and we can kind of continue on with our journey here. Now, if there's an error, how are we going to handle that? So we have so this does not return a pixel color, so what we could do is we could return a error pixel. We could say that like so the has value, we could give it a, I believe we made it a uint32. There's a lot of ways we could do this. So one way is up here. We could do struct voe for voxel error. Actually, we don't really need a struct air. Well, maybe we do. I don't know. Well, we'll make it a struct just to be consistent with how with the nesting order, right? So if these all nest, we shouldn't have a variable that doesn't nest as a member of this. I think that would just be easier. So we'll just call this vo, and we'll just do vo and voxel air info. And yeah, so we'll call that voxel air info right there. And this will just have a float 32, and we'll just call it MSG air. And the reason why we're calling it MSG air is it's going to be one of these values here. So these air 1, air 2. So we're going to define a new air. We're going to do define air 3, which is going to be 3. Right? And with our air object, now that Vox00 has like an air thing in it, we'll go to here and we'll just say vox000.voe for voxel air dot msg air equals, and then air 003, right? So we'll set an error message into this so that we can kind of handle that later. And now I don't really know if we need to do that though, right? Because it's very unlikely that I've made a mistake here. So maybe, you know, after we're done doing this, we'll like comment this out and be like, yeah, we don't make this mistake or something, and just reuse air 3 for something else, because we don't have many slots for creating errors, right? Because we're using very specific pixel colors for our errors, so we don't want to be wasteful with how we do that. Set error set voxel okay. With that, we need to figure out what x bound, y bound, and z bound are, right? So we know that it's going to be the first pixel of the next voxel is what these bounds are going to be. And we already know what voxel we're in. So what we could do is, if we're just going to assume that we're always marching deeper into the voxel space, we can just add. But it's not going to be quite correct, but I mean that'll be a start for how we want to do that. So let's take let's just keep on working on it, and let's not worry about it being not precise, like not 100% correct, because we got to have something to work with first before we can fix it up, right? So equals f32tx plus 1.0, so it's the next tile, right? Is tx an integer? Oh, tx is already an integer, it looks like, yeah? Yeah, tx is already an integer, so we could do tx plus 1. And we could do f32 tx plus 1. So we could do this, like f32, right? So when we are inside of the first tile, that tile is going to be 0, and then npx, right? That'll multiply by 0. That'll give us the first pixel of the first tile. And if we want to go to the next tile, we'll add 1, right? And then tx equals 1, and number of pixels on the for the x. And oh wait, npx, is that the number of pixels in a tile? We want to make sure that it's yes, number of pixels in a tile. We want to make sure that we use that properly. So this will give us the first pixel in the next tile, and we can just do y and z bounds, right? And tx, ty, and tz. So now the question is, well, what if the ray is going backwards, right? What if it's going in a different direction and it's not going down into the space where it's like what if the ray is not what if the ray is going backwards? What if we're not marching forward into new tiles on the x, y, and z, right? Which could really happen really easily. For example, for the Z, we're probably never going to make that mistake because we usually have the camera kind of like at the top looking down into the tile map data. But for like, for example, X, this will probably change depending on if the camera is kind of like panned right or left. Depending on if the camera is panned right or left, the next tile on the X will be decremented rather than incremented, right? So this is not so we have to figure out, well, how are we going to fix this formula so that it accounts for that. And one idea is we can take the sign of the camera ray. We can take the sign of the camera ray and convert it to a positive if it's positive, and a negative if it's a negative, right? So just a negative or positive 1, right? Now, if we do that, we have to think about, well, what is the implication for the math over here? Like, will it just all nicely work out, or will things get like kind of fucked up on us? And I don't know. So let's think about it. And the distances. Okay, so the first thing is, if we're going to allow the x-bound to not always be positive, right? The x-bound can sometimes be behind us, right? And that's going to be accounted for by the ray going in the opposite direction. So what we got to do is we definitely have to do abs, right? So we got to take the absolute value of these deltas, right? And for this plus ones here, what we're going to do is we're just going to take f32 how are we going to do this? How do we take a value that is a negative or a positive and just turn it into a -1 to 1. Turn float into 1 or -1. So I don't know how that's done. So let's, I'm going to make a note in my shortcuts here. And I'm going to say, turn float into 1 or -1. Turn float into sign. Extract sign from float. So, I mean, the easiest way to do that, like a non-mathematical way, would just be, you know, F32 sign equals, my float greater than, or, oh, yeah, so what happens when it's 0? Greater than 0, question mark, and if it's greater than 0, we're going to do 1. Otherwise, we're going to do, my float, less than 0, question mark, and then we'll do a -1. And otherwise, we will do 0, right? So we can do something like that. And this might look kind of confusing because we have these nested ternary values, which, yeah, definitely makes things confusing because it's if greater than 0, we do 1. Otherwise, do this statement, right, is what it's saying. And I've tried to organize it so that all of these like statements like this are kind of very uniform, and then the else with the 0 is kind of on its own. That way, if we want other statements, we can just like duplicate. Okay, so let's take that and let's just put that in some notes here. So, float to sign. Okay, so this is just my float to sign snippet, which I'm going to use. I could have a syntax error there, but I think that is correctly written, and we'll just find out. So, okay, and yeah, let's take that, and we got in our shortcuts now. And we can also like have a little reference in our shortcuts. We can actually take the literal source code and we can just paste it into our comments just to make it kind of like easy to reference. Where like, well, what's inside of here without having to open up the file. I can just paste that into my shortcuts and I can kind of see it. So that can be helpful. And let's just, I don't know, let's just make a little dashed line, I don't know. Okay. So with that, we need to make these ones into either a 1 or a -1, and then we actually have to think about, well, what the hell do we do if it's 0? If it's 0, it doesn't move, right? If it's 0, it doesn't move, and if it doesn't move, it can never intersect, right? So if it's 0, it needs to not be, so this right here, we need like a sine x. We need another and for like if sine x not equal to 0, right? Because if it's not equal to 0, then we can't, there's no possible way for us to figure out where we're going, right? So I see my math isn't quite correct because my math right now is just accounting for which edge is the closest, and that's not going to be right all the time. So let me show you what I mean, so I can kind of see that we have some other problems. Here, let me think about it. Um, so yeah, there is a problem, and we'll figure it out as we go. But let's think about so let's take these signs and let's just see if we can so we need like a float 32 sine x, right? And it needs to be related to this. And what we're going to do is we're going to use the px value, right? So if px is positive, that means we're moving forward into higher x tile values. And if the py is higher, if these are positive, then the tile values on the x, y, and z are going up, right? And if these values are all negative, then we're decrementing the tile values, right? So let's take px, and we'll just p dot x, and we could I don't know how we want to indent this. It's just kind of like some crazy kind of code, anyways. And we just want to duplicate that, hope that this isn't syntactically incorrect, because if it's syntactically incorrect, then we're kind of wasting some time. X, Y, and Z. So for these signs, then instead of adding the 1, right, we're going to add sine of x, and then we're going to add sine y, and then we're going to add sine z, right? And we can indent here and just say sine signs of ray vector, right? Signs of ray vector is kind of what that means, right? P is this x, y, z, and also that is incorrect. We're not looking at P, right? P is our point in space. We want that to be the ray world normal. So let's change this, and let's change this to R. and then we'll just go define R ray world normal. Now, this could be a questionable practice of making these defines like this, because we're adding an extra level of like mental interaction, you know, and that might not be what we want to do with this. Like that might be inadvisable. The reason why I am adding this extra level of mental interaction though is because P fits nicely here in our little ASCII diagram, right? And R could somehow fit in here as well. So we're just doing that to that terseness locally, so that we can just kind of keep track of everything going on a little bit easier. So signs of ray vector. We're going to take this and we're going to kind of like subdivide this section, and then we might want to make like a little comment of like, what is signs of ray vector for, and mention why we're using it. So we need to know if the ray is moving forward to higher tile values or backwards to lower tile values, right? So that's all we're doing here. Now, I'm sure there's probably a more mathematically pure way to do what I am doing right now, but you know, I'm not a super awesome mathematician, so we're just going to do it in the way that is the most straightforward, and if we come up with a better solution later, we could possibly code that as well. So let's make sure that these X's and Y's and Z's are all correct. So if we highlight them, we see unique groupings of colors, so we know that's correct. Just a little checksum, right? And then we could also highlight this in like a purple or something, make sure that those S's are in the correct spot. So just a little quick glance there says we haven't made any transposition errors, and we can kind of continue. Okay, with that, we have these signs, and right, so if so when we're trying to calculate where we are, we'll take that tile X, and we'll either add or subtract 1, right, to get the next tile value, right? And then we times by the number of pixels on inside of one tile to get the pixel coordinate, right? Because we're actually doing everything in frag chords, right? And that's why I want to do everything in frag chords, because it just makes it really easy to reason about the space, because I can actually think of everything in terms of like a gigantic pixel canvas, and think of all the voxels as tiles that are a certain number of tiles in size. So, so this math makes sense to me going forward. Now the question is, what happens when we go backwards? Or what happens when this is 0, right? When this is 0, we just have a problem on our hands, because if we add, well, if we add 0, we just end up in the same tile, right? So 0 is going to be a problem, but let's think about what happens when we go negative. If we go negative, do we get the, are we consistent with where that border should be? So let's look at our camera again. with that, let's kind of keep on going here and see what else we can fix up here. So this formula here is good, right? So we might want to say consistent C so I'm gonna consistent. I don't know how to spell consistent because I can't spell worth shit. So consistent. Okay, so that looks correct. So I'm gonna say C consistent voxel chords, right? And over here, we're just gonna make a little diagram for this section. Okay, so consistent voxel chords. So we're going to take what we kind of drew on the graph paper, and we're going to put it into the source code so that, you know, later after I've thrown all of this graph paper in the trash because it's taken up so much room, I can see, like, what that reasoning was. So the reasoning that we wanted was just... and let's see if we can... So obviously it does take a large amount of time to, like, draw stuff in ASCII, and so some people will forego this, but the idea is I want to make sure that... oh, that looks kind of nice. I wasn't expecting that. So... for this... So let's say -1, 0, so 2. The tile map math for calculating what voxel/tile we are inside of is geometrically consistent even when given relative numbers, meaning the first pixels of any voxel are in the same relative position, right? And so right here we could say first edge of pixels for voxel/tile seen on the x, y axis, right? So that's all we mean when we're trying to talk about for what we're doing here. This is what we're talking about, right? So now that we have this consistent voxel chords thing, we can kind of like go back to here, and we can keep on working, right? So we have all this code, and if you're confused about what the hell this means, you can go to this comment, right? You can go to that comment, just go Control F on the comment, and you can find the diagram section for it, right? And that's just helpful because we want to, as I heard somebody on LinkedIn say once, having a whole bunch of comments and diagrams in code can kind of just be like having, writing like a, it's kind of like writing random notes inside of the gearbox. I don't know how they set it, but yes, comments can definitely clutter things up. So we should try to offboard comments sometimes. And like this, like maybe eventually we want to offboard this, but for now we're still kind of thinking and reasoning about this, so I'm not going to offboard that quite yet. So this is distance to next voxel, so that makes sense that that's indented. I'm just looking at my indentation levels. Okay, so now the question is, how do we figure out which wall we're going to hit here? Because it's not really, right? Because we know that this isn't right. We know that these calculations here aren't correct, right? Knowing which wall we're closest to is definitely going to be helpful. But it's not gonna, it's not quite the right math. It kind of sounds like we need to, okay, so there's, so these are the distances to the edges, and there's one more calculation we need, right? And that is, how are we going to do this? So I think having some type of fall through might actually make sense here. So I'll show you what I mean. So I think, God, this is going to be written in a really wonky way, where people are going to look at this and be like, what the hell is this? But we're just going to go with it. So screw that. I'll get rid of that. Screw that for now. So while loop GLSL. Okay, so a for loop, a while loop, okay, so we're going to do this. We're going to do a do loop, and then a while 0, right? And that means that it's kind of like, well, why are we doing a do and a while? Because a while 0, because aren't we just going to, it's never going to loop, right? It's never going to loop, and that's correct. So we're kind of going to create something like a switch statement with fall through, but it's so this might be better suited for a switch statement. Let me think about it. Yeah, because we probably could do like a break inside of a switch statement, but have like an optional break. But I don't really know how that works in switch statements, and I'm not used to doing that in a switch statement, so this is how I'm going to do it. So, in here, finding which edge is closest is definitely a sign that, you know, we're onto something, right? Unless the distance to intersection is further than one tile away. Does that make sense? Hold on. That might not be quite what I need here. Let me look at this for a second. Okay. Hmm. So, works with the Z as well. So, because right, this is three-dimensional. So we need to account for that as well. So that kind of sucks. So maybe are we thinking about it too hard? Like if we find the intersections, is it really just the closest intersection, right? Like we might not even need any of that, right? Maybe it's just the closest intersection. So if we look at if I'm just gonna draw something again and just say, well, is it just the closest intersection? And um well, it's the intersection within the bounds, right? So if we tried to be more lazy about it and we just calculated all the intersections, then it's just the intersection that is closest to us, wouldn't it? It's the it's not even about it's not really about what is the closest. So, I think I'm totally wrong about thinking about what's closest. It's what wall we're intersecting, right? Um that's all we really care about. We don't really care about how far away any wall is. Why are we even thinking about that? Yeah, it doesn't matter how close a wall is. All that matters is what we're going to intersect next and where that intersection is. Okay. And then we also have the problem of the zero. Um, okay. Actually, that's really easy. Yeah. Um, okay. Yeah. So actually, what we can do is let's look at our camera again. back to the camera here. So this ab stuff with the abs and the bound, that's just not quite. We definitely want to intersect these bounds. Oh, I see. Okay, so these are the bounds that we want to hit, and we need to. This might be more variables than is actually needed, but it's best if we can absolutely kind of think about this. So let's comment this out, because we're probably about to throw this in the trash. But I haven't committed to getting rid of that just yet. Okay. So we need a bounding volume. So we'll do like v2 and we'll call it bounding volume bvx. So bounding volume x equals vec2, and what we'll do is we'll take it's really just the okay, so we really don't need that. So when we're looking at a bounding volume, right? So let's draw out our voxel kind of thing and show you what's going on here. So let's make another little diagram so that we can kind of understand what the situation is here. So okay, and do it. Okay, so we're inside of this voxel. And I guess we could try to get that to be a dashed line. So when we're looking at a voxel, we want to look at the first. We want to be aware of the first edge of pixels that are surrounding this voxel, right? And when we're trying to find an intersection point, we want to find the next actually, let's just take this and see if we can just okay. So if you are here, let's say OV for origin voxel, or cur voxel. Yeah, we'll do like CV for cur voxel. Okay, so let's say we're inside this current voxel, and when we're calculating the bounds of what is kind of like valid. Let's just move this down. Let's put a breakpoint. We're gonna need more space. So this is gonna get out of hand really quick, because really what we need is okay. So when you're inside of this voxel right here, when we're calculating the intersection points to get to the next voxel, that intersection point needs to be like inside the dashed regions, right? And it should be exactly this has no thickness, so that sucks. Let's see if we can do a cutaway view. Let's see if we can make this these a little bit thicker. See if we can do like a cutaway view and try to give the region a little bit of thickness so that we can illustrate that we kind of need to be in there, right? So okay, so within here, we can get rid of these, because these are not the current voxels. Oh, wait, but we can't get... Hold on. So I actually want to just remove the middle part, right? Yeah, I just want to remove the middle. And then we'll take this, and we'll kind of... I don't know what the hell I'm doing here. I'm just trying to, like, cut and paste stuff, and I just cannot do it. Okay. So I think... Okay. So... assuming vectors are moving in a positive direction, the intersection point point to next voxel must be within the bounds of the current voxel plus 1 pixel all around. Right, so this is our like 1 pixel border all around, and we're saying that this is the current voxel right here, and then 1 pixel all around is this stuff over here. So these guys right here. So we're kind of expecting that we're expecting this one section of pixels right here. We're expecting the intersection to be somewhere on one of these pixels denoted by a 1, right? It's this 1 pixel. So this is the entire voxel here, and we're expecting to be like over here somewhere, right? And because we know the direction of the ray vector, we don't need a bounding volume and can just check that the check that and x that the respective x, y, z bounding planes have not been exceeded, right? Okay, because we know the direction of the ray vector, we don't need a bounding volume. We can just check that the respective XYZ bounding planes have not been exceeded, right? So, bounding next voxel bounding volume. Next voxel bounding. It's something like that. I don't know if that's the best description. Next voxel bounding volume, but that's just what we'll call it for now, unless we have a better idea for another time. We'll just give it that name. That name will work for now. So let's take that and let's copy it. Let's go to where we were kind of like doing this stuff, and so the z-bound, so these different bounds are all we really need, I believe, right? Because we got the tx plus the sine x times the number of pixels. Does that make sense? Yeah, because it's gonna give, because this will give us the that first pixel kind of bound. So the intersection point okay. So basically, next voxel bounding volume. This is a nice little diagram here. So, could actually take. So let's take that like this, and is that the correct indentation level? Dist to next voxel. So we're kind of like here, and yeah, so we should actually be kind of like indented one more. To be kind of like, if we want to be like consistent with our indentation. Jesus Christ, I can't type. So if we want to be consistent with our indentation, we gotta indent like that. Okay. So this x bound, y bound, and z bound, we don't want to exceed that. Oh, I guess the reason why we might want a bounding volume is because if the value goes negative, then when the value goes negative, then the x bound is also goes negative. So as long as we, even if this number is a negative, like because we're going into negative tile values, it should still work. I think. Hold on, or maybe that won't. Okay, no, it won't. So, let's look at the camera for a second. Go back here and kind of see like, well, how are we doing this? So yeah, so it's gonna be easier if we just I feel like there has to be a more mathematically consistent way to do this without like using a whole bunch of branching logic. Um, I have to think about this for a second. So this signedness really isn't correct, right? Because, well, we want to check the intersection with, so if it's positive, then this makes sense. Does it really matter? Does it really matter, if we create a volume around where we expect the intersection to be, do we even need an exact x bound? Well, if we don't have an exact x bound, then we have to calculate intersections on both sides, on both x boundaries. That doesn't make sense. Why would we want to do that? And if it is 0, we haven't even addressed, well, what happens if it's 0, right? Well, it never intersects. It never intersects if it's 0, so I don't know if we have to worry about that. Off by 1. Okay, so this is just gonna get ugly. That's all. Yeah, alright, whatever. So, unfortunately, it's just, this code's just gonna get ugly, but let's just, we gotta solve the problem first. Let's not worry about how ugly the solution looks, because, you know what? We just need the solution first. We can clean it up later. The problem is that this logic only makes sense when the yeah, this only makes sense when it's positive, because otherwise our boundary is, we have, yeah, okay, yeah, so what we're gonna do is if r dot x is greater than 0, or greater than or equal to 0, we'll say, else, right? And if rx is greater than or equal to 0, then x bound will be this guy. And otherwise, x bound is going to be float 32 and It's going to be tx plus I'm going to try to make this shorter because we're running out of room here. So I'm going to take this, I'm going to make a little comment. And then we're just going to go put a B in front of these for bounds. So BX, BY, whatever, right? So it's almost, so we're going to take the first pixels of the current tile we're in, and we're just going to, because the ray is going in the negative direction, we're going to minus 1.0 to get to the last pixels of the previous tile, right? That's kind of ugly. I don't know, because the whole if else, but I guess, this is kind of ugly too. So, maybe I'm just so technically this is still that's still this stuff, right? Okay. So with this, we're going to take it, and we really just need to duplicate it and just do the same thing for Y and Z, right? So we're just going to take everything, cut, paste, kind of pretty simple, right? Just okay, so now after we've kind of like cut and pasted, we want to make absolutely sure that we haven't made any transposition errors. So we'll color everything that is X one color, and then we'll do everything that is Y a different color. And then everything that is Z, we will do a different color as well. Oh, I screwed that up. So let's try that again. So this color, that color, that color, right? So this color, that color, that color, right? Once again, this color, that color, that color, this color, that color, that color, right? So everything that is X is cyan, everything that is orange is Y, everything that's yellow is Z. So we can check here, and by taking this little extra time to make sure that we haven't messed up our X, Ys, and Zs, trust it'll save us a whole bunch of headaches later on. So that looks correct to me. Okay, and so now that we know that we have these bounds, that all I need? So I'm just diagramming some stuff out here and seeing if that's right. Actually, it's going to be a lot easier for us if we it's actually going to be a lot easier for us if we do all these calculations. So what I'm talking about, so let's take this, so F32, would rather not. Okay, so what we're going to do is we're going to get some more chunks here. X-bound min. So these are our mins, and then the ones will be maxes. And then, obviously, it can't be B. It has to be like this. Okay. And for these, what we're going to do is we're going to actually keep all of these. So we're going to keep we're going to keep both of these formulas. And we know that 1 is the maximum, so this is the x1, because we're adding 1, and also because it's the higher border, and this is the lower border. So we're going to create like the entire bounding volume. And now if Rx is greater than 0, then Rx greater. So let's do something like this. So Bx equals R dot X greater than 0, greater than or equal to 0, question mark. And if that's true, then we're going to take the positive bound. Otherwise, we'll take the backwards bound, right? And then we can keep that a little bit shorter as well. So this Bx is the boundary that we want to collide with. And then this is going to be the entire bounding volume that we need to make sure that we're inside of. So after we've collided with Bx, we want to make sure that that collision point is within this volume here. And if this collision point with Bx is not within inside this volume, then we discard that intersection, and we're like, that intersection cannot be correct, right? And then we'll do By, make sure it's inside the bounding volume, etc., right? So with that, we can take, so the way I like to do things is I like to do them in a very batch processy kind of way. So group all of the like things together. So this By and then this By goes over here. And this is going to be our, and let's just put the Z over here. And let's just group all of the similar things together. And why I want to group all the similar things together is because it just makes it easier to see patterns in the code if we group the similar things together. And it also makes it easier to just see mistakes, right? So I have a very batch processing kind of mindset when I'm doing things like this. So we have the these are the X, Y, and Z, and they are the ones. So we'll take X, Y, and Z, we'll paste it right here, and then those are the ones, right? And then the zeros, X, Y, Z, and these are the zeros. So we can just take that, paste that there. So these are one set of bounds. And then for the other set of bounds, right, we just need this logic. If the array is going forward, we take the high bound. Otherwise, we take the low bound. And on the case of if it's 0, then we still take the high bound. And I don't know if that's the correct way to do it. I don't know if that's the correct way to handle 0, but I think that'll work. So now let's just kind of like replace all of the, right? Because now we can just easily replace the x's and y's when everything's grouped together nicely like that. So with that, we have to look at some of our math here. So integer plus an integer times another integer cast into a float. Integer plus another integer times an integer. We cast a float, then we minus 1.0 to get the last pixels of the previous tile. So this is the current tile, and this is the pixels, the first pixels of the current tile. And so if we minus 1 from that, we're going to get the last pixels of the previous tile. Okay, so with that, that looks like a decent formula. It's a little bit more variables than I wanted, but we're not going to worry about using too many variables. We want to have the problem well defined, and if we want to kind of optimize that later, we can do that. But we want to make absolutely sure that everything makes sense to us first, because it doesn't matter if we optimize it if the code's wrong, and it doesn't matter if we optimize it and we have no fucking clue what's going on. So the first priority is just getting code that we understand, getting code that works. It needs to work, and we need to understand it. That's the first priority. We can worry about making it more optimized later, once we have code that actually works, that actually functions how we want it to function, right? And then this is also x, y, and z. So x, y, and z, x, y, and z. Okay, so all of the x's are cyan, y's are orange, z's are yellow. And by just doing a little check there, it looks like everything is consistent, right? So by keeping our code as regular as possible, we can avoid mistakes, because of the regularity the regularity of the code gives us visual regularity that makes it really easy to spot mistakes, right? We have like all these 1s lined up, we have all these 0s lined up, we have all these 1.0s lined up. So everything's very regular. Now you might say that, you know, these operations could probably be just put into like a probably like 3 lines of code, right? Because we could put this if we had npx, npy, and npz, and they were all inside some type of vector, and then tx, ty, tz, if they were all inside of some type of vector, then right, this would be trivial. This would just be collapsed into one operation. This would be collapsed into one operation. This part wouldn't be, because we're looking at the individual components, though. So this is more verbose than what might be necessary, which I am often quite more verbose than what is necessary. Okay, so now that we kind of know that what we're going to do is we want to collide with bx, by, bz, and then we're going to test those collisions to see if they are inside the bounds, right? And if they're not inside the bounds, then we'll discard them and go to the next. So we can get rid of this, because that's trash. And we can get rid of this weirdness where those calculations were wrong. My assumption about just looking for the closest edge was ill-founded. But as I was calculating closest to the edge, I believe I did come to an insight about how to find those intersections, so that's good. Okay. So we'll do those. We'll do the intersections now. So we'll do float 32, scalar x, scalar y, and scalar z. I believe we had like variables for this earlier, but we kind of like deleted them as we were working. But we actually need these scalar variables again. So scalar x, y, and z. And what we're going to do is we're going to use point normal form. We're going to do point, the point in space, plus the normal times the scalar. Let me see if I can zoom in there. So the point in space plus the normal times the scalar. And we're going to set that equals to, so if we're trying to, say, hit the x bound, whatever. So what I mean is we only care about the x component, right? So basically, for solving intersection with the plane, we want p dot x plus, we can just look at n dot x, right? We can just look at one component times the scalar equals x bound, right? So that's so that is kind of what's going on. We're gonna take the let's see if we can make some more room. Right, so that's kind of what we want. So this is the general form of kind of how I was thinking about it first. And we might want to just call it B for consistency with our code. And also because it'll make it terser and easier to keep within our bounds. Whatever. Whatever and whatever, you know. Blank and blank. Blank equals don't care about. Okay, so the blank equals that I don't care about it, right? So these blanks equal I don't care about it. And for getting the intersection with that bound x, we'll take the point, we'll do point normal form, and we'll set that equal to the bx, right? And so now we'll, well, we're setting it equal to this vector, which has the x component, but we don't care about these, right? So since we don't care about these, we can just focus on the bx, and to focus just on the bx, we can just take the x components of those things and set it equal to that, right? And so the next thing is just some pretty simple algebra, right? So we're going to take the n dot x times s equals bx and minus p dot x. And is that how I have it in my notes? Yes, that is. And then after that, we're solving for the scalar value, right? Because the scalar value is how far we're going to go along that ray to hit the boundary we are looking for. So with that, the next thing is we just need to isolate s by dividing both sides. So equals this, and we'll take this and bx minus p dot x, and we'll just divide it by n dot x, right? N dot x. And so let's double check that math, because I am horrible with math. I make a lot of mistakes. So point normal form, that checks out, and we're going to set it to the to where we want it to intersect. So this is just the x component of the resulting 3D coordinate from here. So we want this 3D coordinate that results from point normal form to for that x value to match up, and we don't care about any of the other aspects, right? So now we're just taking that exact formula, and we're just isolating the x values, so we're kind of simplifying it in a way. So from here, we're just going to minus that px, and we have the minus px over here. Okay, that looks good. And then we want to isolate this. Multiplication needs to turn to division. Okay, yeah, so that looks good. I think that formula looks good. And we want to just okay, so now that we have this We'll just put this in some comments so that we can reference this for now. Okay. And this would be, this would actually be S, would be scalar X, scalar Y, scalar Z. So let's just use a proper vec for this so that we can keep the diagram a little bit more consistent with what the code says. So we'll do a vec3 S and scalar Okay, so scalar for point normal form. And so this formula is correct as it is, but then we're just going to take the exact same stuff and we're just going to append the dot x to it, right? With that, we're kind of like running out of space, so let's just kind of save some of the space by kind of like moving that in a bit. Okay, so we have this general formula, then we're only going to do the formula for x, so we're going to isolate the x's, and then we're going to solve for the scalar's x value, right? So that looks good. So now with that, what we could do is this formula, we could actually solve everything in that formula really quick. We could just say that the scalar equals this boundary, so bx, by, bz. We could do a vec3 bx, by, bz, and then we could minus a vec3 of p dot, well actually p dot, p is already a vector, right? Yeah, p is already a vector, right? It's the xyz. So this is kind of like, I don't know. I don't know. I think that just makes the code even more confusing. Right. Let's just solve the equation 3 times. You know, whoop-de-doo, right? Whatever, 3 extra lines of code. So s dot x equals b dot x minus p dot x divided by n dot x, right? And so we just got to take that and duplicate it. Right, so basically we can create a vector with the bounds, right? We can plug all of these bounds into a vector, and then we could easily solve for it. So we've made this one line that could be s. It could be s equals b minus p divided by n, right? S equals b divided by p, or sorry, minus p divided by n, right? And if we wanted to, we could keep our comment like that. So s equals b minus p divided by n, right? So that way we have a comment for it. That's what this code is here, right? We're kind of verbose, but that's what it means. We can double check our colors, make sure that everything's correct, looks correct. Okay. So with that, and we have these scalar values, we definitely have what we need to find those intersections. So now we can do we can calculate all of the um, so now we need intersection. So what we need now is we need v3 intersection x, and that equals well, can't we just take the shortest? Well, we can't take the shortest because so initially I'm like, okay, well, we can just take the shortest value, right? We can just take the shortest scalar value and then we're done, right? I'm not sure if that's correct though. So let's try to draw something where we can invalidate that, where we're incorrect. Or maybe that works. Yeah, that might actually work. The shortest. So rather than we might not actually need to see if it's in the bounding volume. I think we might just be able to take the shortest distance that intersects, and that might so it's not the shortest distance in terms of the point to the okay, so let me show you here. bounding math was ill-guided, and we don't need it. So we don't need, so we still need bx, by, bz, but I don't think we need these guys. I don't think we need these guys. So this is kind of like extra math that we don't need. We could use this to check our math, right, and check that the results are within the bounds, you know. That also could be helpful to make sure that our results, so we could still use these values to check our math after we're done here. But yeah, so all we need is these bounds, right, and we're going to just check to... Okay, yeah. So, intersection x, yeah, we don't need any of this, right? Yeah, so, we do need intersection x, y, and z, though, but, we don't need it for each one of these planes. We just need it for the plane that we've chosen. So, if sx is less than or equal to s dot y, and s dot x is less than or equal to s dot z, and we still need to think about what happens when we have a 0, because a 0, a vector with a 0 could this could mess us up. So we still need to so let me make a to-do note here. To-do. What happens if a vector component is 0, right? So we still want to know, we still want to have we still want to address this. We haven't thought about it, so we still need to think about that eventually. So, if Sx is the closest intersection, because it's the least distance we had to travel, then oh, interesting. So, next, first pixel of next voxel. So that's what this is. So we're going to be a little bit verbose. We're not always this verbose, but first pixel of next voxel equals a vec3. And then we need to solve some equations here, don't we? So we know the scalar value, so we just need to plug in point normal form into this. Oh, wait, you know what? Let's make it a little bit simpler. So, okay. So we'll do F32, shortest scalar distance. Shortest scalar distance, right? And so we're going to take this and we're just going to duplicate it a few times. Okay, so SX. Now we're going to do SY and SZ. And SY and SZ. And SY less than X and less than Z. Less than X and less than Y. Okay, so now let's make sure this all makes sense. So the first this should be X's at the beginning, Y's at the beginning, Z's at the beginning. So the colors here should match the colors here, right? Because X, Y, Z. These colors match these colors. Now the second term should not match the terms that are right here. So we have two different colors, two different colors, two different colors. Okay, so that's correct. One thing we're missing, though, is I can see these colors are all the same here. So we forgot that. Control 0. And now we can, make sure we can highlight these one more time. Make sure that everything is consistent. So this is going to determine... so we have cyan, cyan, and cyan, right? So the first term here should match the color here. First term matches the color here. First term matches the color here. So that looks correct to me. So the shortest scalar distance. And then to calculate the first pixel of next voxel, the first pixel of the next voxel. And so we might want to change our ray marching algorithm to actually give us the next actual point to jump to like snap to, rather than using distances. And the first pixel of the next voxel should be like this formula, right? So it should just be... and actually, you can probably just do P plus N times S, right? We could probably do that, and then we can just use a define for the S. Oh no, we already had the S here, so so that's kind of verbose, but you get the idea. So, and it's basically what we're looking at here is P plus N times S dot X or S dot Y or S dot Z, right? That's kind of what we're looking at here, right? If we want like a more terse version of what that is. Okay, so with that, I think we have a pretty good crafted formula here. The next problem is what happens if there's 0? What happens if one of these vector components is 0? So I'm going to just kind of draw that out on some graph paper and kind of think this through. Go look at the code for a second and think about what happens. Do we get a divide by 0, right? Because that would be bad. And indeed we do. So if we look here, we can see where we're solving for the different scalar values. We have this divided by normal.x, normal.y, normal.z. So if the normal is 0, then we just don't want to do anything with it, right? And in order to do that, how are we gonna calculate that? Is that the only place that we're going to have a division where you have to worry about that? Yeah, that's the only place we got to worry about. So, one way we could solve this is we could, if we wanted to be really hackish, we could add like a very small value to these normals to make sure that they're never quite zero. However, the problem with that is now that's very hackish. That's not quite correct. So I don't know if I like that. So we're just going to wrap these in. Okay, so what we're gonna do is we're just gonna have to wrap it. Unless you have a better idea. So if n.x is if 0 is not equal to, or 0 if 0.0 not equal to n.x, right? And we will, it'd be really nice if we could just keep that all in the same line. Okay, you may find this practice kind of questionable, but this is what I'm going to do. Oh, wait, you know what? I don't know if that's the way the logic works with, I don't know if you can do booleans on float. So, define nx as n.x, or 0 not equal 0.0 not equal to n.x, right? So we might as well just ny 0.0 not equal to n.y, and then define n.z 0.0 not equal to n.z, right? And then we can use that in all of this. So we can just wrap all of these expressions. So n, okay, x, y, and z. Okay, so now let's make sure that those colors are correct. Oh. So that looks good to me. I don't think we've made any transposition mistakes here. But it's good to just take that extra time to be a little bit careful. Okay, so that looks good. And then in our logic over here, right, if we never calculate sx, x, y, z, then they're probably going to be like 0 initialized, right? And to eliminate some ambiguity there, we might want to 0 initialize it. So S3 equals V3, 0, right? V3, and it's a 0. Okay. So we have a vec3, and we're going to just initialize that to 0. So now the problem is, when we're doing these comparisons right here, well, if we don't have an intersection because this scalar is if we don't have an intersection because nx is 0, right? Then this scalar never gets set, and then the scalar ends up being 0 because we initialized everything to 0, and then the thing that absolutely doesn't intersect gets decided as that's what intersects, right? And so this would be absolutely horrible mistake. So what we need to do is we need to just do the macros for the NX. So NX, and then for here we got the NY, and then over here we have the NZs. Okay. And with that, NX, NY, NZ, the next thing is we might want to, so when I use a define, I really do like to indent, but we're like running out of room here. So we can't. We don't have any room to indent any further right now. So, technically this is referring to, let's create like a section here, and first right, so first pixel of next voxel is kind of what this section is all about. And I like to kind of glue my defines to the section headers that I create, so it's just easy to kind of like see these sections. And okay, the section name has the same name as the variable. That's really not a problem though. That'll just make it easy to remember what I'm talking about. So this to-do here, what happens if vector component is 0? We just figured that out. But there's one other thing we might want to consider before we're completely set that, you know, oh, we figured it out. So these bounds, right? I believe these bounds depend on whether or not these are 0 or not. And looking at these, well, it doesn't fucking matter, right? Because if these are 0, right? Then we're never gonna calculate the intersection with them anyways. So if they're 0, we don't even calculate the intersection. So it doesn't matter if we choose this or we choose that. It doesn't matter because we're just never gonna calculate intersections with it, right? So so I noticed that I named this NX, and I got NX like all over the place, but I don't see N being used anywhere. In fact, it looks like when I used R here, because for Ray World Normal, it looks like I ended up switching to using N instead later, right? Yeah, so I started using N later, and it doesn't look like N is actually defined anywhere. So the way we're going to fix that is we're just going to change this R. We're just going to change anywhere to R. We're going to change it to N for normal, because that's, I think that is more sensible. So it's only in those locations right there. So we're going to do, and let's take this and point. Just a little note that this is point normal form. Right, that's why I want to keep it as P and N. This is why I want to keep it as P and N, because we're doing point normal form, so P and N actually makes more sense. So over here, we can just take this R for ray, and we're going to do N for normal, right? Because we're looking at the normal's direction and kind of calculating what we should do from there. So greater than or equal to 0. And then over here, we'll do the same thing, so N, and then we can also make the note that this is point, and that this is normal. Right? Point normal form, that's what we're doing our calculations with. So with that, I think everything looks pretty good. The next problem we have is, let's just put a breakpoint right here so we can kind of come back to this. And the problem right now is that we didn't design, originally we didn't have this design in mind. We were thinking what made sense was the distance to the next voxel, right? And we were thinking, let's just do that. And now we're kind of like, you know what, instead of distance to the next voxel, let's actually just figure out the first pixel of the next voxel. So, how are we going to fix that? Well, we actually have that information, don't we? We have that information if we want to use it like that. So let's go F2 and look at where we've kind of set our breakpoints, our little notes. So why is n? Why is this just an n, right? Because we just did. Okay, yeah, got ya. So what we can do is so what we could do is we could do vox 000 dot voxel distance dot distance to next equals shortest scalar distance. And then yeah, so we really don't need the first pixel of the next voxel, right? This calculation here. But we won't get rid of it yet. That's an optimization where we can get rid of stuff. But let's say distance to next is the shortest scalar distance. Okay, so that looks good. Now, there's the possibility that we've made some mistakes in our code. And so the next thing I want to do, because I liked how that worked, and I thought it helped me find problems, is that we're going to do a once-over over everything we've just written, because we've just written a hell of a lot of stuff. And we're going to do a once-over on it. And the goal is that we're going to read this entire function, this function here. We're going to read it out loud from the start to the beginning. And we're going to make absolutely fucking sure that there are no syntax errors, right? And if we are that careful looking over this function, then I think that that it'll give me more confidence that there are not any mistakes here. Now the thing is just because there's no syntax errors doesn't mean that there aren't any other mistakes. However, if I try to run this right now and there's a syntax error, and I tend to make a lot of syntax errors all the time, then that's kind of like a indicator that there could be other types of errors besides syntax errors. Like if you were so careless as to make a syntax error, what makes you think that somehow you were so careless to make just a syntax error, but all the other logic, no, you weren't careless about any of that other logic. It was just the syntax errors, right? Like, that's highly doubtful. So let's take a look at everything and kind of account for everything. So We have this tx, ty, and tz. So tx, ty, and tz, and tx, ty, and tz. So that means they also need to be undefined eventually. So if we look at down here, tx, ty, and tz indeed are undefined. Now, we want to make sure that within this function that vox000.voc.tx is actually a thing that is there, right? Because we did some refactoring, and if we look at here, we see that we have this voc thing, and vox00 dot voc .tx, ty, and tz. So it's indeed there. So this is the nice thing about naming the struct exactly the same name as the variable name, and naming all of the components the exact same name as their struct types, because it was very easy for me to follow this code and see that everything was in the correct place. So it's important to note that these are integers. So when we're looking at the math here, we can see that this is assigned to an integer, so that's good. This is also integer math, so that's good. I'm not too worried about these things being wrong because these aren't changed from the last time. But n x y, x y z, that makes sense. This is the two-dimensional index. This is the three-dimensional index. So VAT is VAT accounted for. So VAT should be like our tile map data. Yep, that's our tile map data. So that looks good. What else? Let's just kind of color code everything until it's all colored, right? We'll just kind of like cross it out with purple once we've kind of looked at it, right? And we know that that is good. So the signature, does the signature look correct? Well, we have the U's, XYZ, and RWN. So we know that XYZ and RWN are definitely the inputs for that. The output is definitely the Vox00 type, so we're good there. Declaration, so we're just going to zero initialize, or I don't know if it's zero initializes, but we're going to allocate the object that we need to return at the beginning of the function, which is a good convention. The voxel value is set to a negative trap value to say it's an invalid value. We'll set it later. That's a good convention. I like that. Integer is 0 minus 1. A little bit redundant, but it helps us read the code and realize without looking at the definition of val, we know that it's an integer as long as this compiles. So these, right, the last cast is to integer. We can make sure that the brackets are balanced, and the brackets appear to be balanced. This is x, y, and z. This is x, y, and z. So the x, y's, and z's, they match up. And we're trying to figure out the current voxel cell. So it's just normal tile map math, where we do xyz.x divided by a float npx. Okay, so we had to xyz, so this is already a vector, and this was a define, so we had to convert that to float, then we floor it, and we turn it into integer. So this math is pretty standard. It's math that I'm used to, and the math makes sense, nothing odd there. Also, I already checked earlier with some graph paper to make sure that when the values go negative, that the math still makes sense and is still consistent. And this tile map math will still be consistent with negative values. Let's continue. Obviously, you'll get tile values that are negative as well, right? So you get tile -1, -2, which are out of bounds tile values, but the values that it maps to are consistent even with the negative. Okay, over here, we're just making sure that we're in the bounds. If we're in the bounds, then we can figure out what voxel we have. So tx, ty, tz, number of tiles x, number of tiles y, number of tiles z. So the first thought is, why is it a less than? And it's less than because if we have 100 tiles, then we need to be less than 100 because the x value would be from 0 to 99, right? Because we start numbering at 0. So that's why we have a less than rather than a less than or equal to. So that makes sense. tx can be 0, so we have a greater than or equal to, so that makes sense. And this is a x, that's a y, that's a z, so the x, y's, and z's, they all match up. So we can kind of put that in purple, and we can say that that part's good. Let's check our braces. Our braces, they look good. So the formula here, right? We're going to take the number of tiles on the x and the y. And why are we doing this? So that's kind of, so this is kind of confusing, and I'm not sure if it's correct. So the index 2D, we're finding a two-dimensional index, and then we're going down to a three-dimensional index. Oh, wait, so the number of tiles on the x, so this is standard tile map math, right? So the number of tiles on the x, and then we're going to multiply by ty, right? And that'll give us the correct position with... Yeah, so okay, I know this is standard tile map math. So we're just looking at the x and y value, and we're just trying to figure out the index if this were just a two-dimensional tile map, right? And so this is kind of like a leftover index that we have to add to the three-dimensional index later. So yeah, actually, this makes sense. This is your normal two-dimensional tile map math. So this is the index in a two-dimensional tile map. And then we have to remember, oh, wait, but we have some extra layers, right? There's some extra layers worth of tiles. So when we take tile x times tile y, that's an entire layer's worth of tiles. And if tz is 0, then we don't have any extra filled layers of tiles, right? If tz is 1, we have one full layer of completely filled tiles as a completely filled layer. So this is the number of completely filled layers, which creates extra index values that we use to offset the two-dimensional index to get the three-dimensional index. So that math is actually sensible, right? X, Y, and that is actually sensible. So number of tiles X, number of tiles Y to get the volume of a cross section, and then figure out how many cross sections deep we're going. That makes sense. Number of tiles X times TY, because for every Y you have a full row of X's. Makes sense. And then X is just whatever is left over. That's why it's a plus. Okay, so that makes sense. So this, we've checked it. We've checked the sanity of this multiple times. We are absolutely fucking sure that is correct. So let's, so I don't know if we just cleared all of this, but we know we're over here and we've checked everything above. So let's just keep going. So the voxel dex, right, is that three-dimensional index, and the voxel val is just looking up that value with that index, right? So we're doing a little bit more lookups than we need to be. We're probably being wasteful with our memory, but we need something that works first, and we can worry about cleaning it up later, right? So with that, let's take a look and make sure that dex and val are actually in the VOC object, right? So if we look at our struct again, we can see our voxel object, we can see the VOC, and if we go to VOC, we see that there is a dex and there is a val. So we're good there. Now the question is, are they both integers? So are they both integers? This is an integer, and for this tile map data, that tile map data should also be an integer. So if we go up and we look at the vat object, this guy right over here, we see that it is an integer array. So that is good. So let's keep on going. We can just color that. That's good. Now, the other thing we want to do is we want to make sure that our comments are balanced. So we haven't checked our comments yet. So let's check the comment characters here. So we got blue and we got yellow, or orange, blue and orange. Everything looks lined up there. This is a uint value because it's just supposed to be a boolean that's true or false, and I don't actually want to use it in any formula logic. That's why I set it to unsigned integer to make it a little bit harder for me to accidentally use. And we can check to make sure that that exists as well. We can go back up to our object, make sure that has is inside the vox object, and we see the vox we see the voc, and inside voc, we have a has value that's a uint, so that is also good. Okay, and we have a nice little diagram here, and let's just make sure that the comments are matched, comment characters match. So we have P, and then I is like the intersection. This is the Y bound. This is the X bound. And it's kind of confusing because, like, you know, this is a vertical line, and we say X bound, and this is a horizontal line, and we say Y bound, and that can kind of get confusing. But it's where this is an unchanging X value, right? The Y is changing, but X is not. And over here, Y is not changing, but X is. So I think that's basic geometry, I think. Okay, so now we have this P and the N. So let's look at the P and the N and make sure that they're all in places that make sense. So P and N. So we shouldn't see any N's or P's referenced above here because they're just not there. And N's, some more N's, normal times a scalar, right? Normals. So solving for these scalar values, using the normal values, that looks good. Point, normal form, so point plus a normal times a scalar, that makes sense. And then making sure that we undefine what we defined, right? So as far as that, I think that we've gotten past this part where, you know, that makes sense, and we're kind of like over here now, right? Do we have any comments instead of comments here? No, we don't. We're good. A little diagram that's been offboarded somewhere. Okay, so we have this bx, by, bz, b0s, or not b0s, but let's just color code them all and check them out really quick. So our upper bound is just taking the current tile value, which is an integer, adding a 1, multiplying also by integer the number of tiles. And that will give us the pixels that we're trying to intersect when we're looking forwards with array. And that makes sense. We also have to convert it to a float 32. Are these float 32s? Yep, these are all float 32s. This is similar math, except we're looking at the current tile we are on, and then we're just minusing 1, right? And we did cast this to a float 32 before we minus this floating point value. So that looks good. Okay, so the bx, by, bz, all the colors are lined up. And if nx is greater than or equal to 0, we're going to look for intersection with the upper bound. Otherwise, lower bound. Same thing with the y, upper than lower. Z, upper than lower, greater than or equal to 0. That's all of them. If it's 0, it really doesn't matter which we select if it's 0. So that also looks good. So let's keep on going and see what else we can check, make sure that everything looks good. So first thing is I want to check these comment characters and make sure that they are balanced. So yellow, purple, yellow, purple, yellow, purple. So that all looks good. We don't have any comment characters inside here, so that won't be a problem. And okay, that's still good. So this is just kind of diagramming the math that we did. First pixel of next voxel, nx and y. Okay, so these are just defines to make the logic easier. 0.0 not equal to nx. So this is just so we can avoid the divide by 0 errors or divide by 0 mistakes. So let's color code those and see if those are all in the correct place. So xyz, xyz, xyz. And let's just color code all of this as well. And then we'll also analyze the... that was not how I wanted to do it. So let's do that over again. So x, y, and z. And then x, so this is a scalar, and we're trying to figure out what the scalar value is, right? And then we have these formulas. And once again, x, y, and z. And this is x, y, and z. Okay, XYZ, XYZ. Okay, so these formulas, we kind of solve them further up here. So bx minus px, and then divided by nx, right? So we can check that logic one more time. So point normal form set to where we want the x value to be for the collision with the plane. And first part is just to subtract. Well, first part is we're going to isolate the x's, then we're going to subtract the p's from both sides. Okay, and then after we do that, we want to divide nx out of here and put it on the other side, and we have divided nx. So we know that this formula here, right here, this formula is good. That formula is good, so we just want to make sure that is that the formula we're using down here. Sx equals bx minus px divided by nx. So yeah, this is the correct formula. Let's keep going. So this scalar value, is it declared before it is used? It is referenced in this diagram, but then it is used directly below here. So it's declared in the correct space. We don't have any semicolons at the end of this define. And, oh, so I see a mistake. So right here, we put this at the end, and at the end, my convention is to have undefs. So undef, and then nx, ny, and nz, right? So if we do this, we might want to also make sure that nx, ny, and nz is not some type of special define somewhere else in our code. So let's just look over where else we may have used nx. And I see we did have an nx in this diagram here, but I don't see anywhere else where it is defined or where it even exists as a variable. Now, that doesn't mean that we don't have something similar for ny and nz, though it's very unlikely because of the way I do my math. If we have a variable for one, we probably have a variable for all the others as well. So, looking through this, it looks like we're good as far as avoiding variable collisions. The reason I want to be careful with that is just because these are all capitals, and you'll notice that if we look at some of these defines up here, we have like ntx, npx, tpx. So, you know, at one point in time, I could have decided to make this like nx, ny, and nz. And I could have decided to make this tx, ty, and tz, right? So I just want to make sure that there weren't any collisions over there. So that looks good. And let's kind of continue through this. We can remove this breakpoint and kind of continue down a little bit further. These bounds. We already checked out these bounds, did we not? Yes, we did. Let's look at this again. Integer math, all integer math, casted to float. That's good. Let's keep on going. We can remove this breakpoint, and now we're kind of like over here, and we just looked at these formulas. These are the formulas we looked at. They're pretty consistent. We got x, xyz, 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 xyz. Okay, so shortest scalar is this distance, and first pixel of next voxel. And if we look at these, why don't we color code them and see where they are? Okay, so if nx, so this is just our guard. These are our guards to make sure that that component of our vector of our normal is non-zero, right? Because if it's 0, it's never gonna move forward. It's never gonna collide with anything, right? So x is wait. So this is a little bit trickier. So it's not just a. It's not as blind as everything just lines up, right? So, because I was like x, y, z, y, x, x. Oh, we made a mistake. No, we didn't. So, this should be x, y, z. This should be x, y, z. But then these columns here are going to be slightly different because the x needs to compare with the y and the z. The y needs to compare with the x's and the z. The z needs to compare with x and y, right? So these first parts need to be correct. So what we could do is we could kind of highlight this like that. Actually, let's do that. So let's go 0. And we can highlight including the and symbol to still see the pattern. So, so 1, 2, and 3. And then we can go 1, 2, and 3. And we can see that these should be the same color, and these should be different colors. So Y and Z, and we want to make sure that these two are different letters. Y and Z, X and Z, and then we have a X and Y. So that looks correct, and that's the shortest scalar distance equals either X, Y, or Z. So that is correct, so we're good there. The first pixel of the next voxel, we're going to take the point, and we're just doing point normal form. So point plus the normal times the shortest scalar distance. So what would be good right now is to make sure that this normal this normal and this point are actually what we think they are, right? So we are kind of like down here, and so we're getting close to like having looked at all of this code. But let's look at the point and the normal and make sure that they're defined correctly. So if we look at these defines, the point is the XYZ and the normal is the ray world normal. And that is the input right here, the XYZ and the ray world normal. So that is correct, so we're good there. What else? So after that, right, we're just going to assign to the distance next variable. So I think that is something we recently made a change. So I don't know if that actually exists. Okay, so it does exist because we have distance to next. Oh, so we are just kind of discarding the first pixel of next voxel, right? So we're not using anywhere. Not using this anywhere, but keep for now. Now is not the time. Right, so right now, ooh, god damn it, F12? Yeah, there we go, F12. So let's make sure that these match. Okay, I got 3 and 3. So yeah, we're not using this anywhere, but we want to keep it for now because it helps us give us some context of, you know, what this value is that we are loading into our output variable. And with that, I guess the next thing is to be, this looks like it's an outer scope. The distance to the next voxel is in the outer scope. Does that make sense? And actually that does make sense because we subdivided our space. We subdivided the space into voxels. So it doesn't matter if we're outside of our voxel map, like all of space is voxels. Even the negative cells, right? Even the negative voxels are still voxels. So this still applies even if we're like way out of bounds of the voxel bounding volume, right? So we're trying to subdivide all of the space into voxels before we even determine if we're inside or outside of the bounding box of the voxel volume, right? So, and we're doing that because if we want proper voxels, then the actual space that we exist in should be volumetric pixels or volumetric elements or whatever you want to call them. If we were to have a different coordinate space and we were to do everything in normalized device coordinates, then we don't really have voxels, right? If we do everything in normalized device coordinates, then we don't have voxels. We have like this. We don't want to like be doing polygon math. We don't want to be swapping back and forth between polygon math and voxel math, or you could say a polygon coordinate system and a voxel coordinate system. We do not want to do that because then we're kind of like we're adding extra layer of interpretation because we got to convert between those two spaces, and then we have to reason about those two spaces. So we just want to think of everything as voxels in three-dimensional space. Also, with that, we do have two spaces to reason about because voxels are composed of pixels, right? So I know a voxel, to people, they usually think of a voxel as a three-dimensional pixel, but I'm thinking of my voxels as three-dimensional tiles. So I'm thinking of, So the Planck unit of my coordinate space is the pixel, right? So I'm thinking of all of the space as pixels, and then before I do any voxel type math, I divide all of the space into voxels, even the space that is outside the voxel map. Okay, anyways, I'm talking to myself. I don't know if anybody will ever listen to this, but anyways, that's kind of what we're doing here. And let's take that and, I don't know, go with it, I think, because we're really close here. So voxel distance.distNext. Let's make absolutely sure that that is correct. So if we go up to where distNext is, we see vox.voxel distance. Inside of voxel distance, we see distNext right over here. So that is also good. So we have these undefs, nx, ny, and nz. Those are correct. Actually, we fixed them earlier, so I know they're correct. And yeah, so that is pretty much good. That's like, that math is the math we want. Now, the next thing we should look at is, because I make the mistake a lot, is do we have semicolons exactly where they belong, right? So we'll do one more pass, and then we'll say that we've checked this thoroughly. Got the semicolons, semicolons, semicolons. Okay, no semicolons needed. Yep, good. Good. We could just color the semicolons, right? Make them stick out. And that way we can check, because if we don't see one somewhere. Good. Good, good. If we wanted to, we could, it might be ill-advised, but we could also line up these semicolons. And that makes them more obvious of where they are. If we want to get really, really weird, if we want to have some fun, this might actually be a bad idea, but if we want to, we could go like this. We could go line those up. I think that's actually going to make it harder to look at. So I don't know if that was a wise choice. But hey, let's just roll with it and, you know, experiment, see what you like, see what you don't like, you know. Okay. So x bound, y bound, z bound, right? So we have this little table of what these values are: bx, by, bz. They're all float 32s. And now we can really easily see where that we have semicolons where they belong, just because and I believe we can actually be at liberty to do extra semicolons, right? So technically, some of these semicolons do not belong because, well, see this empty line? We just have a semicolon on a blank line. Sometimes a compiler will complain to you about that. I believe it's okay inside of a function, and that just makes it really easy for me to see, do we have a semicolon? Yeah, we have semicolon. So that's just stating, that is basically stating to me that I see this line, and I can just assume that, okay, all of these statements are just one-line statements. And because we have this right here, and we can easily account that all of these semicolons are there because there's just this big line of them, right? Okay, so comment characters, that's not really what we're looking at. We kind of already decided that comments were okay. This looks like a mistake. So it's kind of good that we're looking at semicolons now. So look at this formula. Oh, okay, no, the formula is inside of a branch. So that's why we have a semicolon here. Because we've taken something that might span more than one line, depending on how you write it, but we wanted to line everything up nicely. And therefore, this is the end of the statement where we're assigning s.x equal to something. And then we're also closing off the branch with, or we're closing off the scope with a semicolon. That might not be necessary. I don't think you actually need a semicolon at the end of scopes, but I usually do. Except for the end of function declarations, where my C compiler will always yell at me for doing that. Semicolons here. Else. And then no error case, but we'll be fine. And okay, and I just feel like lining these up, even though they're never going to match. I just feel like lining them up, and that's another thing I can check for. I can check to make sure that these never match. So ZX, ZY, YZ, right? They never match. They shouldn't. That's a questionable, right? When in doubt, I line it up, because that's just how I am. That looks good. Shortest scalar distance. Okay, and oh crap, what time is it? Did I have that? Did I reserve? Ah, crap, I reserved that for 1 p.m. and it is like 3:38, so I totally missed this. I should just keep on reserving things for 6, because that seems to be when I'm used to doing it. Okay, so let's not worry about that. That was just a reservation I missed because I was busy doing this. I think Friday maybe I couldn't get later because it's Friday. So shortest scalar distance. That looks good. The balancing is correct. So this is a float. The normal is a float. Shortest scalar distance should also be a float. Yeah, float 32. And we have the semicolons. When you see double semicolons, that just means that the statement spans more than one line, and that's just my way of noting that. Okay, yeah, so that looks good. So this is the math here. I think it's good. I could be wrong. I could have made a mistake, but I don't think there's any syntax error. So that's maybe we'll clean this up right there. Now you make sure that the function does not have any semicolons at the end of it, and we don't actually intend to actually use any of the data from what we've just done. I mean, we're going to use it eventually, but we just wanted to get that logic correct before we even use it. So this Vox, okay, so eventually we're gonna like ray march inside of the voxel here. That is a to-do. So what we could do is, while we're here, let's make a, to-do. All right, and I make the to-do span my column limit, so it's really obnoxious and annoying, and I like absolutely know it's something that is offensive to me because it's going past this hard limit that I've established for myself, and I'll violate that hard limit because it's something that absolutely needs to be addressed. So when the code is finished, nothing should go past this column limit. So that just lets me know that's my way of doing something kind of obnoxious and outside of the norm, so that when I'm like scanning through this code really quick, I can tell, I can see that little blip, right? And I can be like, right, and blip. And also, let's look at something else, because I saw another little blip that I wasn't happy about. So this right here, we kind of already solved this. We already decided that this was correct from last time when we were doing the code. So we can actually remove this offensive stuff right here. Okay. And this right here, this is kind of, we don't really want to change any functionality, but we don't really want to go past our limits. So what we're going to do for now, I think, I don't know. This would be, the dirty solution would just be to do that, right? I don't really like that. So let's, we definitely want to fix this indentation. So let's say, so we do want to fix this overflow below, but I don't believe in anything, I don't believe in such a thing as a trivial refactor. So even though I just want to reformat this code maybe and just kind of like get it to not take up so much space and not go past this line. I don't believe that there's such thing as a trivial refactor, so we don't want to address that just yet because I just don't think I don't believe that we're not going to make a mistake. So if not defined, define f32 float. Now that define is in quite the wrong spot right there because so let's get rid of the example code. And this, if not def, yeah, like that's completely useless where it is. Integer modulo. So I32. So what we'll do is we'll take the we'll just take this if not def for the integer modulo, and we'll just add that to the top of this section. So this doesn't really affect anything because it is it's code for if I want to copy and paste this integer modulus code later, and I want to copy and paste it to another project. You know, we might need these if defs in case I don't have a header where I declare these top-level macros for the code. So we'll just, yeah, we'll keep it like that. That's fine. And now we have some more commented out stuff because we had bad assumptions from yesterday. So we're just cleaning up messes from yesterday, it looks like. And we got to be very careful when we're cleaning up these messes. Make sure we're not, like, you know, doing anything that's going to change anything. Okay, so that looks good. And just be very careful when you're making these changes. Even though I'm not actually changing any code, I'm just, like, deleting some lines that are just comments. I still want to be very careful because you want to compile often, write a little bit of code, compile, write a little bit of code, compile. We're kind of breaking that rule by going around and cleaning stuff up. So that looks good. And if we keep on scrolling and we see that other to-do here. So let's look at this. Do we have, with this Vox, okay, so we should end up with the code working just like it was working before. It's just that now we have kind of like the logic we need for a voxel array marching kind of like stubbed in. So I'm going to hope that this works and that we haven't made any mistakes. Actually, I'm going to do one more thing. I'm going to check down here, make sure that there's no make sure there's no comment characters inside of the main comment block. It doesn't look like there is. Okay. So we're going to run this, and hopefully it still runs. God damn it, still made a mistake. So what is the mistake we made here? And it better not be in the function I looked at. Come on. Oh, yeah, okay, yeah. Yeah, okay, so I see what we did, and god damn it. I was so hoping that I would have, like, not made this mistake. So I make this mistake all the time. I guess it's because I saw these zeros and ones here, and so I instantly thought, well, then this doesn't have to be... Yeah, so this is a 0.0. Because they are floating point values. And... Alright, well, we've already looked over this enough times that, you know, we're just going to have to keep on trying to compile it and run it until the mistakes are gone, and I hope that was the only mistake, because I really looked at this Okay, yeah, so that was the only mistake, and we can see that we still have the same output. So let's go into the dolly. So let's go to the dolly, and make sure that dolly still looks the same. I expect the dolly to still be the same, but let's just put that dolly animation back in here, and just see that that looks how it should look. So let's take it. Alright, so that still looks like I would have expected it to look. And with that, I think it's a good time to... I'm going to take this code and I'm going to post it onto... I'm going to update my links, right? I'm going to update the pastebin URL for all this, because now we're at a good kind of like checkpoint. So I'm going to go to paste bin, and I'm going to edit that paste bin, and I'm going to put the new code there. And this is SDF11, save changes. And I'm going to scroll up here and make sure that, okay, so this looks all nice. Okay, cool, so that's all good. And with that, it's time to take a break. Like we've kind of, I might want to take a bigger break. I might actually want to go for a walk. I've been trying to go for a walk every day, so, I'm gonna go for a walk, brush my teeth, maybe eat some food. I don't know. But yeah, I think that, it's about this is about 4 hours. Yeah, it's almost 4 hours on the dot. And 4 hours is a pretty good session. So when I get back, we'll take a look at this, and we'll try to start doing some more ray marching. And we're going to keep the raid marching very basic. So we are not going to, we are not concerned with what is inside of the voxels. We are only concerned with, are we hitting the voxel or are we not hitting the voxel, right? And if we hit the voxel, is there anything inside the voxel? If there's something inside the voxel, we're just going to render some type of flat color. And if the voxel is empty, we're going to keep on moving and until we either decide we've ray marched too far and we give up, or we hit a voxel that is non-empty. So okay, so I'm going to be back later, but I'm not going to set a timer because I'm actually going to go for like a 30-minute walk and all that stuff. So it makes more sense to stop the stream and then start it after I've taken my break and stuff. So later.